Okay, let's go ahead and get started with the blood vessels. So just starting with some objectives, I want to make sure we understand the functions of blood vessels, be able to differentiate the types of blood vessels, understand pressure changes in the circulatory system, and understand venous return. So starting off with blood vessels, in general, they are the delivery system of dynamic structures that start at the heart and then end at the heart. Coming from the heart, we have the major arteries, the aorta. We learned about that in our heart lecture. And those arteries then deliver oxygenated blood and different nutrients to tissues throughout the body that need them via capillaries. And then from the capillaries, everything that is not needed by those tissues, such as waste products or whatever blood that was not needed by those tissues, is then fed into the venous system. And so within the arterial system, the arteries leading right up to the capillaries are known as arterioles. So they're a little bit smaller than arteries. And then the veins that stem right off of the capillaries that lead to larger veins are called venules. All right. So looking at systemic versus pulmonary circulation, here we can see that there are two different circuits of blood flow in the body. In the systemic circulation, this larger one, arteries carry oxygenated blood away from the heart to the tissues that need them in these capillary beds. In the pulmonary system, with the lungs though, this is reversed. The arteries carry deoxygenated blood away from the heart. So it's still an artery, it's still moving blood away from the heart. It's just deoxygenated still. And so we got to find a way to pump that blood to the lungs at a higher pressure. So we get that deoxygenated blood to the lungs, trade it off for oxygenated blood, and then veins bring it back to the heart. So these are the pulmonary veins. So that's the only difference between the pulmonary circuit and the systemic circulation is going to be the type of blood inside of a vein or an artery. It just flips. Other than that, if you think of the systemic system, all arteries and arterioles are going to have oxygenated blood. All veins and venules will have deoxygenated blood. So trying to look at the structure of blood vessel walls, they have a lumen, which is the central canal where the blood flows. They have three layers, the tunica intima, media, and externa. And when we get to the capillaries, they only have an endothelium, which is part of the tunica intima layer. And so they don't have these other layers, they only have an endothelium. And we'll discuss why that is when we get to them. So this diagram is looking at the different layers between the three different types of blood vessels. So the tunica intima consists of an endothelium, which is continuous with the endocardium of the heart, and it lines all blood vessels on the innermost surface, including the capillaries. And that's actually the only layer on the capillaries, is this endothelial layer. It has a very slippery surface to reduce friction of the blood flow, and it's, again, the only layer that these capillaries have. The tunica media consists of a smooth muscle layer as well as some elastin. And this layer is under control of sympathetic innervation. And so what does that mean? Well, it means that this layer is what constricts or dilates in order to change the blood flow and pressure. The terminology associated with this in blood vessels is called vasoconstriction or vasodilation. Notice that the arteries have a significantly larger tunica media because of the smooth muscle layer in there than veins do. So it's a significantly larger tunica media. They'll have a stronger influence on the maintenance of blood pressure than veins do. The tunica externa consists of collagen fibers that help protect and anchor the blood vessels to the structures that are surrounding them. So looking at arteries, they carry oxygenated blood away from the heart, except for in the pulmonary circuit. They are under the highest amount of pressure compared to veins, and this is due to the blood coming right out of the hearts, or the blood coming right out of the heart. And so it's under the most pressure when it first comes out of the heart. And there's a larger tunica media than veins. Again, that smooth muscle for vasoconstriction and vasodilation. Arterioles are simply the smallest arteries that are immediately before the capillary beds, and they control the flow into the capillary beds via vasodilation or vasoconstriction. Capillaries consist of only the endothelium layer. And this helps allow for rapid molecule exchange. So there's not a whole lot of layers for the molecules like oxygen and carbon dioxide and different nutrients to go through. It's just this one simple layer. And that's why there's a very low pressure area in here as well, so that the molecules that are diffusing across this endothelial layer are just diffusing down their gradients. And so the capillary bed consists of a bunch of different capillaries, and they function to exchange these gases, nutrients, wastes, hormones. And it's between the blood and the tissues that the blood is supplying. So oxygen and nutrients cross into the tissues because there is less of oxygen and nutrients in the tissue, and there's more waste and carbon dioxide in the tissue, so it crosses down its gradient into the blood. And veins carry deoxygenated blood to the heart, except for in the pulmonary circuit, and under lower pressure than arteries and capillaries. So think about it as the pressure is changing from the highest pressure in the arteries to a little bit smaller pressure in the capillaries to even smaller pressure in the veins until it returns back to the heart to be pumped out again. Veins consist of these one-way valves promoting a unidirectional flow. They have thinner walls, larger lumens than arteries, and a high capacitance. So these end up being called blood reservoirs. They hold 65% of our blood volume in the body. And so most of our blood is residing in the venous system. And this is because it's under smaller pressure, but they have a high capacitance, meaning that they can stretch. They have a high elasticity, so they can stretch and hold all that blood as it's moving back to the body, or back to the heart, sorry. And similar to arterioles, venules are the smallest veins, which are immediately after the capillary beds. Multiple venules will join to form veins, and they are incredibly porous. They're just like the capillaries, so they're the primary sites that allow white blood cells back into the bloodstream from tissues and lymph tissue. And so looking at our diagram here, you have an arteriole. This would be stemming off of a larger artery. And then this precapillary sphincter controls whether or not blood is going to enter into this capillary bed and supply the tissues that might need it. Or if the tissues don't need anything, it won't constrict. It won't dilate, allowing blood out there, and it will force the blood to just go straight through, like it's shown here. And this is just called a meta-arteriole, which basically means it's kind of like an artery, but it becomes a vein. So it's a meta, kind of like an arteriole. So what I really needed to know on this slide was just what was circled, but I was just explaining this for your own information. But arteriole leads to the capillary bed, and after the capillary bed, it leads to the venule, and within the capillary bed was the capillaries, of course. And this is just a nice diagram illustrating the pressure changes that I was talking about from arteries to veins. If you look at the aorta coming right off of the heart, it's at the highest amount of pressure. And then elastic arteries and muscular arteries are withstanding a lot of that pressure because of their elasticity and their muscularity. And then arterioles are smaller, so it starts to drop off right away. And the capillaries, tremendous drop off. And then venules and veins and the vena cava is when the lowest amount of pressure you will see in the circulatory system or within the blood vessels. And looking at venous blood return, venoconstriction, so just in general, back up, there are 4 different paths or mechanisms that the venous system utilizes to return blood, because it's not under as much sympathetic control as the arteries. It is, but not to nearly the extent. And so there is a little bit of sympathetic control called sympathetic toning. We know the nomenclature designating this is venoconstriction. So this innervation is innervating the smooth muscle layer in that tunica media of the veins to help return that blood back to the heart. It's not super strong compared to the sympathetic innervation of arteries, but it's there, helping provide some level of blood return. Muscular pump, just think of this as every time that you move your body or you're flexing your muscles in any way, they're squeezing on the little veins in there, helping move the blood through those veins. Well, you might be asking, well, why is the blood only moving toward the heart and not, if I'm squeezing my muscles, both ways? There are these valves in the veins that help prevent backflow. And so I can go back all the way to this slide, you can see there's a valve that's not present in the artery, but it's present in the venous system, and the blood only goes through the valve in one way, kind of like the heart has its valves. They're like these semilunar valves here. So you don't need to know the type of valve, but just understand that veins have these valves that allow blood to circulate through one direction. And so the last one would be a respiratory pump, and similar to the muscular pump, it helps squeeze the veins or the blood in the veins back to the heart, but it does so with pressure instead of actual physical like manipulation or like squeezing of the veins. So it does it with pressure instead of the skeletal muscles. And so breathing changes the pressure in your thoracic cavity, and then that allows blood to move into the heart from the vena cava seamlessly. And so it decreases the pressure in that area, allowing blood to just flow in. And it also squeezes the abdominal veins below that thoracic cavity, helping decrease the pressure even more in the thoracic cavity. So basically just what you need to know is what this says is breathing changes the pressure, moving the blood toward the heart by squeezing abdominal veins while the thoracic veins expand. And this is because of lower pressure in the thoracic veins compared to the abdominal veins. And lastly, when it comes to blood vessels, I just wanted to talk about pulse. So what is pulse? It's the surge of blood felt against your artery walls. Well, why don't you use your veins? Well, there's not nearly as much pressure coming from your veins, so we're looking for arteries. And so this is going to indicate your heart rate. And the strength of the ventricular contraction and cardiac output, or how strong your heart is pumping, is what your pulse is. And so if it's really strong, your systolic pressure is going to be high. Your contraction pressure is high or normal. And so a strong pulse is good. But if you have a weak pulse, it means your heart isn't working as hard as it should be, and your systolic pressure has fallen, and you might need medical intervention. Some people just naturally have a weak pulse, and some people just naturally have an incredibly high pulse. But in general, this is the kind of stuff that we're thinking about when we're thinking about pulse.